Hey there, everyone. Welcome back to another exciting GCSE Physics session. Today, we're tackling something super important: work and energy. This topic shows up everywhere in real life, from lifting your backpack to dragging a stubborn chair across the floor. Let's dive right in. In everyday language, you might say, "I'm working really hard." But in physics, work has a specific meaning. It's done when a force moves an object in the direction of that force. The cool part: whenever work is done, energy is transferred. Imagine you're pushing a shopping trolley in the supermarket. The force from your arms moves the trolley forward. As long as the trolley is actually moving, you're doing work on it. But if you're just leaning on it without movement, no work is done in the physics sense, no matter how tired you feel. The equation you need to remember at GCSE level is: work done, measured in joules, J, equals force, measured in newtons, N, times distance, measured in meters, M. You often see this written as W equals F times S. Force is how hard you're pushing or pulling. Distance is how far the object moves along the line of that force. The result is measured in joules, J, which is the same unit used for energy. If you push a suitcase with a force of 20 newtons for 3 meters, how much work have you done? That's right, 60 joules. So, where does that energy actually go? Well, if you push an object and it speeds up, you've transferred energy to its kinetic store. If you're lifting an object, energy goes to its gravitational potential store. And if friction is involved, like rubbing your hands together or brakes on a car, you'll often see a lot of that energy ending up in the thermal store, heating things up. Next time you notice your laptop charger getting warm, remember that's frictional resistance in the circuits, transferring electrical energy into thermal energy. It's still the same total energy, just changing forms. Friction can be super helpful. Think about car brakes, or super annoying, dragging furniture across a rough carpet. In both cases, friction basically opposes motion. When friction does work, it transfers energy into heat. This is why your hands get warm if you rub them fast in winter. In a car's disc brakes, kinetic energy from the car is transferred to thermal energy in the brake pads and discs, slowing the car down. How do you think friction helps a cyclist stay balanced, and where does the energy ultimately end up if they keep pedaling for a long time? Think and provide your answer in the comments below. You can try simple experiments at home or in class to see how work relates to energy transfers. Pulling a toy car. Attach a Newton meter, force meter, to a toy car. Drag it across smooth and rough surfaces. Note how much force it takes and how far you move the car. Calculate the work done, W equals F times S. Compare results. Why do you think the work is different on rough versus smooth surfaces? Lifting objects. Use a mass you know, maybe a small weight, and a ruler. Lift it vertically by a known distance and see how that equates to gravitational potential energy gained. If the object is 2 kilograms and you lift it 1 m, the force you applied is about 2 kilogram times gravitational field strength, which is approximately 9.8 newton per kilogram, almost equal to 19.6 newtons. So the work done is roughly 19.6 newtons times 1 meter equals 19.6 joules. These experiments demonstrate how applying a force over a distance shifts energy from one store to another. Alright, my budding physicists, let's see how you can apply these concepts. Try these fresh scenarios. Do not copy them word for word from your notes, but let them inspire your understanding. We'll go through the detailed solutions in our next video. Pulling a sledge. Imagine you pull a sledge loaded with books across a school field. You apply a steady force of 25 newtons, and the sledge moves 4 meters. How much work have you done, and what energy store is mostly increasing? You lift a plant pot from the ground to a windowsill 1.2 meters high. If the total weight, force due to gravity, of the pot is 12 newtons, calculate the work done. Which energy store has increased? Suppose you push a ball up a short ramp, using a force of 10 newtons for 2 meters. How much work is done on the ball? If friction is a factor, where else does some of the energy go? You push a wooden box with 15 newtons for 2 meters on a tile floor and then 2 meters on a rough carpet. Explain why the total work might be the same, but the final speed of the box could be different in each case. Where is energy going? You lift a 5 kilograms dumbbell from the floor to your chest, a distance of 0.8 meters. How much work is done in lifting it, assuming no frictional losses? Once you hold it at your chest, what's happening with the energy? Take a moment to jot down your calculations and ideas. Share them with us in the comments section below. Work in physics is only done when a force moves an object over a distance. Energy transferred equals work done. They are measured in the same unit, joules. Friction often converts kinetic energy into thermal energy. Understanding work and energy helps us appreciate how tasks become easier or harder under different conditions, like frictionless floors versus sticky ones. Thank you all for tuning in. If you found this lesson helpful, don't forget to like, subscribe, and hit that notification bell so you won't miss our solution video, where we'll walk through these practice problems with step-by-step reasoning. Now it's your turn. Pick one of the practice problems above. Post your answer or your reasoning in the comments below. Let's see how you apply the principles of work and energy. Until next time, stay curious, and remember, the best way to learn is to keep asking.